So welcome back everybody to the little series about how computers work. As always, this simulation is by the YouTuber Sebastian. He made an awesome series about how computers work, but I want to go a little bit further in depth about it, and I also want to take in consideration about transistor count so we can minimize the amount of transistors actually used in case someone wants to replicate it or just for optimization purposes. So this episode, we're going to talk about buses and tristate buffers. So let's go. So we're in the simulation right now. So let's talk about buses first. So what is a bus? So in a CPU, a bus is a shared electrical connection between multiple components in order to share data. For example, you might have a whole bunch of registers connected to a bus in order for them to share data with each other and to give data to the same ALU unit in the computer. And there's multiple different types of buses. The two main ones we're going to focus on is the address bus and a data bus. So a data bus is just going to spit 4-bit data out onto a single electrical path. We're going to have 4 of these electrical paths, each for 1 bit of data, and it's going to be primarily used by registers in the ALU. So the registers is going to input their data onto the bus, and then the ALU is going to receive the data, spit out new data for the registers to restore that data, all on either the same bus or 2 different buses or however many we need. And it allows us to simplify the electrical circuitry, I guess you could say, in the CPU, because we only need one connection to connect everything instead of connecting everything through different components. And then the address bus allows us to determine what register we want to access at a specific time. So if all the register store units are connected onto the bus, we can put in a secret code, which we'll explain a little bit later, maybe in a different video or in this video. And then if the code is specific for that register, it allows us to store data or input data onto a data bus. That might have been a lot of information. This series will easily help you understand it. But first of all, I want to get into a very core concept of a bus. So we know it's an electrical, a common electrical point for gates or components to spit data out. So let's say we have this gate, this OR gate, it's spitting out a 0 onto the bus right now. But if this NOR gate also connects to the bus, it's spitting out a 1. So the bus doesn't know whether it needs to be 0 or 1. And the simulation represents this as a flash. But in real life, it would be a short circuit, and give y'all a little electrical engineering lesson right now. So if the resistance is low between a place of high voltage and a low voltage, the current spikes dramatically up because of the Veer equation, and I'll put that on here. So yeah, because the resistance would be close to 0, and then anything over 0 would go to infinity, so that's why the current spikes up so much. But yeah, we need to fix this somehow. So we need a way to determine what data gets sit on the bus, and then for all the other registers to emit virtually nothing. It's not a 0 or a 1, it's nothing. It's no electrical communication at all to the original component. And in the simulation, it's represented by being black. So a 0 in the simulation is actually this dark gray color, and then nothing is a black color. So if something is a black color, we say it's floating because we don't know what it is. We don't know if it's a 1 or a 0. It's black. There's no connection. It's floating. So I want to talk more about this floating concept real quick because I find it kind of interesting. So we're going to go to a little Arduino simulation so we can see the importance of this floating concept with buttons. Okay, so welcome to the little desk setup that we have here about floating points. So most people, whenever they start off with Arduino, they wire up a button, connect it to the power, and then they have a wire from the button to the digital input on the Arduino. But this is floating. So this is the floating point that we're talking about in the simulation right here. And if the button is pressed, the light's supposed to turn on. But the light doesn't know if it's a 1 or a 0 because the input is floating. So I mean, the way we fix this isn't like in the simulation with the tri-state buffer that we're about to discuss, but all you gotta do is make the input defined, and we do that by wiring a resistor up with the button to ground. So now this wire is connected to ground through this resistor, so the Arduino knows that the light's supposed to be off. And then when we press it, we send a high voltage to the input, and the Arduino can detect that and know the light's supposed to be on. So a little thing that people mess up a lot with Arduino about floating points. So if it's just the input connected to a high voltage with a button, Arduino has no idea if it's supposed to be high or low. But once we connect it to the ground, then it knows. Okay, so now that we got this floating concept down, because virtually as soon as everybody starts with Arduino, we all make the same button connection because we think that makes sense. But actually, this is why it doesn't make sense, because of this concept right here. So how we're gonna fix this is pretty simple. It's already in here, and it's called a tri-state buffer. So we hook the tri-state buffer up to the bus like this, and then we hook our gates up to the input gates. So as you can see, the tri-state buffer is outputting this floating data onto the bus. So the bus is reading nothing right now. But if we enable the enable signal, it allows the data coming into the tri-state buffer to be outputted onto the bus without this one interfering with it at all, because it's not a 0 or 1, it's neither. So we can control what data goes out in the bus. And as you can see, now the OR gates data is going out in the bus because it's this gray color. So we can control what data gets shared around with different components using this tri-state buffer system right here, which is very handy actually. So we're going to delete all of this, and then we're going to make this new chip, which is just 4 tri-state buffers together because we're on a 4-bit system. So yeah, that looks like it's working pretty good. So we're just gonna save this now. So let's see how we can use this in a little circuit now. So let's go back to the our CPU. Let's open this up. So this is it. This is our clock register 2. Now let's rewire it all with the tri-state buffer in a bus so we can see how it works. Okay, so this is a very, very basic circuit of a little bus system we have. There's really actually no point of having a bus for this circuit, but I just want to show how it works really. So what we have these two registers going into this ALU, and then a little tristate buffer to go into this data bus. So other components in a computer could output their data onto this bus, and any of these registers could store the data if they wanted to. So we could have multiple units just like this, all outputting data on the same bus. But this is just one of the units. So we have an enable, so we can enable the bus, and then the number that we have outputted is 12. So we can store 12 into the, well, they both have 12 right now. I guess we'll store in the first one, even though it's, no, the first one is, my bad. The first one is 15. So we'll clock it, the first register stored it, and now we're outputting new data onto the bus, which is 9. So then we can get the second one to store it, and then we keep outputting new data onto the bus, and we can disable it whenever we want to. So a different ALU circuitry can write onto it, and then we can store it using these registers we have right here. And this will come in clutch and handy with more circuitry involved in this. But we still upgrade the CPU, because still we're going to save it onto this. That's a little rundown of how buses work. I guess next video we'll talk about multiplexers probably. And then the video after that we'll talk about the program counter. And then the video after that we're going to talk about how do we write programs in binary. And we'll keep going from there. So I'll see y'all in the next video.